Good morning. I hope you had a nice weekend. So let's begin by talking about the volume element on space-time. And so now we're in a good position to discuss this because last time we showed that one can always choose coordinates in which the metric is equal to eta mu nu at a point. Okay, so recall, one can always choose coordinates so that g equals eta mu nu at a point. Now, if you do that, then in those coordinates, these are locally flat coordinates. And let's call them, I'm going to call them x hat a. Okay, so in those coordinates, the metric is just eta mu nu at the point we're discussing. And the volume element on flat space-time is just dx dv is dx hat 0, dx hat 1, dx hat 2, dx hat 3. Just the usual Cartesian volume element. And this is invariant under Lorentz transformations. Lorentz transformations means x hat a prime is lambda a b x hat b. And then we have the fact that the x hat a d for x hat prime is given by the Jacobian matrix determinant of dx hat prime by dx hat times d for x hat. And this is just the determinant of lambda, d for x hat. And we already proved that the determinant of lambda is plus or minus 1. So if we choose Lorentz transformations which are connected to the identity, their determinant is plus 1 equals d for x hat for lambda connected to the identity. So this volume element is invariant under local Lorentz transformations at that point. So it's a natural thing to use in special relativity. But now we have it in the special relativistic form, we can simply write it as also dv is dx hat 0 is equal to the determinant of dx hat a dx alpha d for x, just using the Jacobian matrix to transform from locally flat coordinates to arbitrary coordinates. X mu. Yeah. Here? This one?
Yeah, is that supposed to have an x now and y?
No. This x is the same as that x.
Okay.
These are the new coordinates. So the statement is that if I have some volume element, d4y, and if y is a function of x, 4 coordinates x, then this is equal to the determinant of dy alpha dx mu d4x. So that's the general statement, right? And here I'm just saying that the volume element is d4x hat. It's the flat 4-dimensional volume element.
Oh, so the hat's on
Pardon?
the hat's on like,
No, they're flat coordinates. Flat spacetime. These locally flat coordinates are x hat a. Is everyone happy with that? Okay, so this is, of course, equal to epsilon alpha beta gamma delta dx hat 0 dx hat 1 dx hat 2 dx hat 3 dx alpha dx beta dx gamma dx delta times d4x. Okay, and that's what I was alluding to previously when I wrote the volume element down, but this is the correct formula. The correct formula for the volume element involves this epsilon and then the determinant of the Jacobian matrix from locally flat to general coordinates. Okay, but the metric itself is also given in terms of locally flat coordinates because the metric, the locally flat coordinate was just a coordinate transformation from the metric, original metric, so I can go backwards from the locally flat metric to the original metric using this formula. These Jacobian matrices are invertible. So the metric is itself given by this dx hat dx alpha. And what we do is define this to be a local frame, E, B, beta, eta alpha A to B. So that's just a definition where E, A alpha equals dx hat A dx alpha is a local frame or Vierbein because it's a vector, it's a space-time vector, has an index alpha, and it has 4 indices A. These are Lorentz indices, locally flat indices. Okay, so this is a Lorentz index. And this is a general space-time, let's call it a general coordinate index. Okay, so in this whole setup, I'm free to do Lorentz transformations on my locally flat coordinates, because they're actually only defined up to Lorentz transformations. And I'm free to do general coordinate transformations on the index x alpha. Okay, so, or the, in matrix form, the metric is E transpose eta E transpose, eta E. And so it follows that minus the determinant of G, well, let's write it this way. If I take the determinant of the metric, that's the product of the determinants of these 3 matrices. So what I get is minus, the determinant of eta is -1. So I get minus det E squared. And so det E, I can even put the indices in, put them in the right order, EA alpha is equal to square root of minus det G. And so dV, the volume element on space-time, is root minus G d4x. Okay, so that's the volume element which we will always use. It's invariant under general coordinate transformations. Any questions? Okay, so this idea of always being able to choose locally flat coordinates is very useful. The only thing you need to be careful of course, is that it really only works at a point. At best, the first derivative of the metric can be chosen 0, but you can't set the second derivative 0. So if you have some equation relating locally flat quantity to a general quantity, you just have to be careful that you're not differentiating it so many times that the whole concept becomes invalid. Okay, so now let us discuss geodesics in curved spacetime. So curved spacetime means I replace eta AB with G mu nu. And the action for a particle is, let's say, a free particle. Means I'm going to ignore all other forces. MC integral square root minus G mu nu. I just want to emphasize this G mu nu is calculated on the curve. So we're thinking about some particle following a curve in spacetime coordinates x mu, dx mu d lambda dx nu d lambda times d lambda. Is there a question? Yeah? Yes. Just look at this formula here, right? So E is a matrix. The little b is the row. Let me just bring that down. Little b is the row, beta is the column. Okay? So let's write that as eta A B E B beta. That's a usual matrix product. Okay, this guy is not the usual matrix product, because I'm summing the row with the row. Usual matrix product, I multiply the column with the row. Okay, so this is equal to E transpose, okay, alpha A, eta A B, E B beta. Now this tells me I'm going to sum the row index of E with the column index. Sorry, with the row. I'm going to sum the row with the row. Yeah? Okay, so the transpose is just to tell you to sum a different index. Normally, when I do a matrix product, I sum, if I multiply two matrices, N, J, K, right? But if I transpose this guy, it's telling me that's what I'm doing. It's equal to that. Okay, so It's just if you want to not to bother to write indices down, you sometimes have to remember to transpose things. How did I get it? Oh, because over there, d4 hat is equal to determinant of E from up there. The x hat dx alpha is E, right? So d4x. And then I use det E is minus root G. Root minus det G. Okay? Any other questions? Sorry if that wasn't very clear. Okay, so here's the action for the point particle. We've studied it before. And now we're going to vary it and get the equations of motion. We studied it before where G was eta. So all I've done is replace eta with G and Minkowski space-time coordinates with general coordinates. This is, of course, general coordinate invariant under x mu goes to x prime mu of x, and g mu nu goes to g prime mu nu, which is equal to dx alpha dx beta dx prime mu dx prime nu g alpha beta. So if I just prime everything, okay, and use this formula, g prime of x prime is related to g of x by this, then you notice that dx mu d lambda is equal to dx prime mu dx alpha d lambda. And then these matrices cancel each other. And dx prime mu dx alpha dx prime mu is delta mu nu. So using that, you can show that this action is invariant under general coordinate transformations. Now let's vary it. Sorry, I didn't hear. Yes. So g prime, x prime, x prime, right? And now then this is dx prime, dx prime, dx. Sorry, dx prime, dx prime times g. And this guy is dx prime, dx d lambda. And then this will cancel that, and this will cancel the guy from here. And so this will equal to root minus g mu nu of x dx d lambda dx d lambda. Okay? So the general rule is if you write down something where all the indices match, use some lower indices with upper indices, then the quantity will be invariant just because the transformation matrix on the upper indices cancels the transformation matrix on the lower index. Okay? So this guy is, so let me write it out again. S is integral root minus g mu nu of x dx mu d lambda dx nu d lambda. So this is the length of the world line. I've introduced lambda, but lambda is completely arbitrary as long as it is monotonic along the world line, because there's a d lambda here and there are two d lambdas here in the square root, and they cancel. So if I change lambda to lambda twiddle of any function of lambda, then this will also be invariant. So let's now vary it. So variation means x mu of lambda goes to x mu of lambda plus delta x mu of lambda. Okay, I consider some slightly different path, and then I work out how the action changes to first order in delta x mu. So this is equal to minus mc. Got to vary the square root, so I get 1/2 1/2. I get 1 over the square root. And then I've got to vary the stuff inside the square root. So let's write that as d lambda over the square root. I've got to vary the stuff inside the root. So this is g mu nu comma alpha delta x alpha. Here I'm varying g with respect to its argument, x. Dx mu d lambda dx nu d lambda. And then I've got to vary these dx d lambda terms. So this is g mu nu of x. There are two of them. The variation is identical because if I vary this guy and then I vary this guy, g is symmetric. So I get a factor of 2 times x dot mu delta x dot nu. Well, let's write it out as dx mu d lambda d delta x mu d lambda. And now what I do is convert this d lambda to proper time. Okay, so notice that d lambda times the square root, in other words, just this quantity appearing here, is the proper time. Okay, but d lambda times the square root is d tau, the proper time. And so this is equal to minus mc integral 1/2 d tau. Now, notice in this expression there are two d lambdas on the bottom, one on the top, right? So there's an overall d lambda on the bottom. So d lambda times the square root is d tau, which means that all the derivatives in here, so in the denominator I've got 1 power of d tau. And so I can just replace this d lambda with d tau and those d lambdas with d tau. Okay? So in other words, here I have 2 powers of lambda in the bottom, 1 power lambda in the top. I have this conversion factor. When I apply that formula, all it does is convert my d lambdas into d taus. So now I'll write this as minus g mu nu comma alpha delta x alpha x dot mu x dot nu minus 2 g mu nu x dot mu delta x dot nu, where dot is d by d tau, d by d proper time. Now, this last term, let's just draw an arrow. This last term here, okay, is equal to integral, so d tau of minus 2 g mu nu x dot mu delta x dot nu. Okay, so yeah, let me just deal with the stuff in the brackets. As usual with variational principles, I have to integrate by parts. to make the answer something times the variation. So this becomes integral d tau. Integrating by parts, I get plus 2 g mu nu comma alpha x dot alpha. Okay, that's d by d tau of g mu nu is just differentiate the g with respect to its argument, x, and then differentiate the argument with respect to tau times x mu times delta x nu. And then I've got to differentiate this guy, plus 2 g mu nu x double dot mu delta x nu. Let me just bring it closer. No, don't do that. Sorry. Sorry. I want the back one up. Okay. Mm-hmm. Yes. Exactly. Yes. So d by d tau of this. So there are 4 different arguments, x0, x1, x2, x3. I've got to differentiate this with respect to each one of them. So that's g mu nu comma alpha of x. This means d by dx alpha, right, times dx alpha d tau. Yeah. Mm-hmm. Yes, from lambda to tau here. Okay. So the proper time d tau is defined to be the square root of minus g mu nu dx mu dx nu. And of course, if there's some d lambdas in here, it doesn't make any difference. D lambda. Okay, so now we've got this form. We can write this as, so delta S equals 0 for all delta X alphas. So it means the coefficient of delta X alpha here, and here, and here, adding them all together, I must get 0. Okay, so the coefficient of delta X alpha here is g mu alpha x double dot mu. So what I've got is 2 g mu x double dot mu. Actually, I've called it, I'll put it alpha just to keep it consistent with that. Okay, so that's the coefficient of delta x alpha. I change the index mu to alpha and set it 0. And then the next term I've got is that, plus 2 g mu nu mu alpha comma nu x dot nu x dot mu. That's from here. So again, I changed nu to alpha and alpha to nu. And then I've got the last term is this one, minus g mu nu comma alpha x dot mu x dot nu equals 0. Now, notice that this quantity is symmetric. Sorry, this quantity is symmetric under mu and nu. So this is equal to g mu alpha comma nu plus g nu alpha comma mu times x dot nu x dot mu, because both of those terms are equal, okay, with a factor of 2. And so now I will divide by the factor of 2, and what I get is x double dot mu plus 1/2. I've got to get rid of that G matrix, so I just multiply with the inverse. G beta mu G mu alpha is delta beta alpha. So multiplying by the inverse matrix, what I'll get here is G mu, and then beta G beta, let's see, the free index is mu, so I know that, sorry, I did, that's alpha. Let me leave it as, that became, yeah, let's call that beta, be less confusing. And then beta mu, g mu alpha comma nu plus g nu alpha comma mu, and then minus g mu nu comma alpha. Okay, hold on a second. Sorry, it's quite hard to do it from so close. Beta alpha, thank you. Okay. Times x dot mu x dot nu equals 0. And so if we define gamma beta mu nu is equal to 1/2 g beta alpha g mu alpha nu plus g nu alpha mu minus g mu nu alpha, then x double dot mu plus gamma mu nu gamma mu alpha beta x dot alpha x dot beta equals 0. Okay, so which is called the geodesic equation. So this quantity, gamma, is called the connection it follows that this equation, you see, the action was invariant under general coordinate transformations. That's more or less how we defined it. So it follows that this equation must be invariant under general coordinate transformations. The geodesic equation is invariant under general coordinate transformations, but its pieces are not. but neither d2x d Tor squared nor gamma mu alpha beta dx alpha d Tor dx beta d Tor, neither of these transform as tensors. Okay. They both transform in such a way, in an ugly way, and such that the ugly term cancels between these two pieces, and so that the result is a tensor. And if it's a tensor in one coordinate system, if it's 0 in one coordinate system, it's 0 in every coordinate system. So let's just see that. So dx prime mu d Tor is, as we've already said, is does transform as a tensor, beta dx beta d Tor. Okay, so that just says that x prime is a function of x, and so if I differentiate with respect to Tor, and really everything is implicit here, so it's x prime of x of tau. So if I do d by d Tor, I first have to differentiate with respect to x, that's this term, and then differentiate x with respect to Tor. So this transforms correctly as a 4-vector. Okay, but the second derivative, d2x prime mu d Tor squared, differentiate again, well, I've got to differentiate this again, right? Everything is a function of x of Tor. So I need to calculate d2 x prime alpha dx beta dx delta times dx beta d Tor dx delta d Tor. And then I've got to differentiate this with respect to Tor. So this is dx prime alpha dx beta d2x beta d Tor squared. Okay? Now, the second term is the correct transformation for a 4-vector. But this term is not. It's nothing to do with the transformation of 4-vector. It involves these horrible second derivatives. Okay, so this is not this is the wrong transformation for a 4-vector. For a 4-vector. But of course, gamma is not a tensor either, because it involves derivatives of the metric. So the metric will go to G prime, which has dx prime dx's in it, but then you differentiate them. Okay, so you're going to get second derivatives from that term too. So in fact, you can check that gamma prime mu nu alpha is equal to the right things, dx prime, dx prime, these are for the lower indices, dx prime dx for the upper index, gamma, let's say, gamma delta epsilon, so the delta epsilon nu alpha gamma mu. Okay, so that's the right transformation law for a quantity with 3 indices. But then there's some wrong terms. dx prime dx, d2 x dx dx prime. This index is rho mu nu alpha. Okay, so it doesn't quite look right because the acceleration term introduced this d2x prime dx squared. The gamma prime introduces this d2x dx prime squared. But in fact, those two quantities are related. Okay, you have the identity dx mu dx prime beta dx prime beta dx nu is delta mu nu. So we have that identity. We're free to differentiate it. So if I differentiate it with respect to x prime, what I'm going to get is d2x mu dx prime beta dx prime gamma times dx prime beta dx nu, plus, now I've got to differentiate all this with respect to x prime, so I'm going to use the chain rule. So this is d by dx prime, right? Gamma. So I get this, then I get the second term. I'll get dx mu dx prime beta, just this first piece in here, times the derivative dx alpha dx alpha dx prime gamma. Okay, so all of this is just d by dx prime gamma, multiplied by or acting on that quantity. Okay, so this is going to give me d2x prime beta dx nu. So this is just d by dx prime of dx prime beta dx nu. So the sum of those two terms equals 0. And what this is telling you is that d2x by dx prime is related to d2x prime by dx. And if you use this equation, you'll find out that this bad term exactly cancels this bad term. Okay? So it follows that, I won't do all the algebra, but it follows that d2x prime mu d tau squared plus gamma mu alpha beta dx prime alpha dx prime beta d tau equals 0. So one equation implies the other. Okay, so the geodesic equation is invariant under coordinates. The geodesic equation is invariant under coordinate transformations, and we learned something very interesting, that this gamma quantity is what converts the gamma quantity is essential to making sure that that equation is invariant under general coordinates. And the way it works is that the gamma corrects for, the transformation of gamma corrects for the bad terms in the transformation of the acceleration. It's called a connection because it allows you to write down derivatives which transform properly. So gamma is called a connection because it allows you to write derivatives which transform correctly. as tensors. Okay, so it's very important that gamma itself is not a tensor. It doesn't transform properly as a tensor. In fact, it's designed so that the error in its transformation as a tensor exactly cancels the error in derivatives. And these derivatives are called covariant derivatives. Covariant derivatives. And they are equal, well, let's say they reduce to ordinary derivatives in a locally flat coordinate system in which d alpha g min u equals 0, all the derivatives of the metric vanish, which implies that gamma alpha mu nu equals 0 at a point. Okay, so if you write down a covariant derivative and evaluate it at some point in a coordinate system which is locally flat, in that coordinate system, gamma vanishes because, big gamma vanishes because the first derivatives of the metric vanish. Okay, so this quantity here is gamma. This is gamma beta mu nu. So obviously, if the derivatives of the metric vanish, then gamma vanish. All the components of gamma vanish. We define a concept of parallel transport. Of a vector along a curve. So if I've got some curve x mu of lambda, and if I have some vector v alpha of x of lambda, so imagine some v alpha, which is a vector field, a full vector field everywhere in space-time, but let's just evaluate it on the curve, on the x of lambda. Then what we can see is that d v alpha d lambda, that would be the derivative of the vector along the curve. This will not be a four vector. The ordinary derivative won't be a four vector. So let's define the covariant derivative. V alpha is the ordinary derivative plus the connection nu lambda v nu dx lambda d lambda. Not use lambda, gamma. Okay, that this is the, this transforms as a four vector. So let me just mention an aside. Particles, free particles in spacetime, free particles follow geodesic in spacetime, and in symmetric spacetimes, okay, and that means in spacetimes which have some symmetries. A general spacetime will just be g mu nu of x, some crazy thing that has no particular symmetry, okay? But in spacetimes that do have symmetries, there are conserved quantities. Let me just say it in spacetimes with symmetries. In spacetimes with symmetries, there are corresponding conserved quantities. Okay, by Noether's theorem. So in particular, if the metric is independent of one of the spacetime coordinates, x alpha. So for example, if this g mu nu of x does not depend on the time, that's a symmetry, because if I look at the g mu nu at different times, it hasn't changed. So if the metric is independent of one of these spacetime coordinates, then the corresponding particle momentum is conserved. Okay, so let me just say what I mean by that. In fact, more correctly, the corresponding conjugate momentum. Okay, so the momentum in Lagrangian or in Hamiltonian dynamics, the momentum is defined as the derivative of the action with respect to the velocity. So we have S equals minus mc integral dx mu d lambda dx nu d lambda d lambda. And so delta S is equal to mc integral g mu nu dx mu d tau d delta x mu d tau. Okay, just using the same trick I used before. I vary this guy, the square root goes in the denominator. I then replace d lambda with d tau. And so the variation of the action with respect to x produces this term proportional to the velocity of x. And so this means that, yeah, in fact, I think there's a c that cancels too, because this perhaps I made a mistake. This should be c detour, right? This whole quantity is c detour. I made the mistake to leave all the C's in, and at C detour. And so the momentum corresponding to this coordinate is equal to m g mu nu dx mu p nu g mu nu dx mu detour is conserved. Okay, so in Lagrangian mechanics, the momentum is always defined to be the variation of the action with respect to the velocity. Okay, so it doesn't matter that g is a complicated function of x. By assumption, I should have got the indices right. Sorry, let me just be careful. G mu alpha dx alpha. G mu alpha. Okay, so I vary this action when I vary it with respect to some delta x for which, with respect to one of the coordinates for which g is independent of that coordinate, then the only variation I get is from here, not from here, right? Because this is independent of that coordinate. So in this expression, there is no sum on alpha on this expression. Okay, so this delta s goes like this. It includes this term. It includes other terms. But the part of it that involves the variation of this coordinate upon which the metric does not depend, okay, looks like this. It must be 0. And therefore, by integrating by parts here, you can see the equation of motion corresponding to a variation delta x alpha is just that p alpha is a constant. So we'll find this very useful in many problems, okay, that if the metric is independent of one of the coordinates, the corresponding momentum is a constant of the motion. So finally, I want to deal with, yeah. Yes. Okay, so delta S is equal to minus MC. Vary the square root. I get 1 over the square root. And then I get minus delta G dx d lambda, right? And then I've got to vary these guys. So minus G d delta x d lambda d dx d lambda dx, sorry, d by d lambda delta x dx d lambda plus, or minus G, the other one, dx d lambda d delta x d lambda. Okay, so I varied everything. Now, here I had a d lambda, right? This d lambda cancels one of those. In the denominator, this quantity together with that makes c d tau, right? C d tau equals the square root times d lambda. And I think I forgot the c in the geodesic equation derivation. Should be a c somewhere up there, okay? So basically I can just replace all of this with d tau, d tau, d tau. Okay. Now, this particular variation I did, I'm assuming G was independent of that X alpha. So this variation is 0. And then over here, I just have this delta X alpha. And these are all taus. Okay. Good. Any other questions? Now, one of the kind of awkward things about that derivation is that it relies on the mass of the particle, right? The action was the mass of the particle times the length of the world line. And in fact, I introduced that as the definition of mass. If you want what is the definition of the mass of a particle? It's the coefficient of the length of the world line in its action. But what about massless particles? Okay, with this definition, the action would be 0. I mean, actually, for two reasons: because the m would be 0, but also if massless particles, their momentum is null, and so I'm taking the square root of 0. That's okay. That's 0. But it's a little weird. Certainly, what I did in dividing by that square root is a bit weird. And I certainly can't redefine the time to be tau. So let's just understand this a little more with the goal of understanding massless, how massless particles move through space-time. And I'll do it the following way. Okay. So a general definition, let's say a more general definition, and this more general definition will be useful because we will use it to understand what happens to massless particles. Definition of geodesics, which also applies to massless particles. Is as follows. We consider a curve x mu of lambda with a tangent vector dx mu d lambda. And so obviously this tangent vector, which is a vector, is a 4 vector, points along the curve. The geodesic equation is the following statement, that the covariant derivative of the tangent vector, okay, and by this I mean this parallel transport derivative I defined before, the covariant derivative of the tangent vector should be proportional, so this is a 4 vector, should be any function of lambda times the tangent vector. Okay, so I've got some curve, it has a tangent vector. The definition of a geodesic is it's a curve for which the change in the tangent vector, the covariant derivative of the tangent vector, is in the direction of the tangent vector. Okay, so the tangent vector, this is saying that the curve is as parallel to itself as it can be. Okay, i.e., the curve is parallel to itself. So in particular, the tangent vector can change in length. We haven't defined its length. We haven't said it's null or it's time-like or anything. It's just a tangent vector. We're allowing it to change in length. Okay, but we're only allowing it to change along along the tangent vector. This, yeah.
So the tangent vector here is like
It's just this. It's just this. So psi mu equals dx mu d lambda.
the main thing is that as if you could say like it's double. If you were to double like how far you went for a given lambda.
Yes, yes. So we're not giving it a length, because actually we want it to be null in some cases. So in which case we can't give it a length. So null vector by definition would be g mu nu psi nu equals 0. So null vectors have no length. So better not use that in the definition of anything. So we're allowing it to change length. Okay. So this will allow us to consider geodesics where, well, will allow us to consider tangent vectors that change in any way we like. They can go time-like or null or space-like. And so this is the more general definition of a geodesic, and it applies equally well to time-like, space-like, or null vectors. Now, this is very general, and in particular, we've said nothing about lambda. Lambda could be any parameterization of the curve as long as it's monotonic, right? So your lambda should increase as you run along the curve. Now, in particular, it's useful to pick an affine parameterization of the curve. Okay, so an affine parameterization is defined as follows. The affine parameterization is defined precisely so that that term goes away. Okay? The affine parameterization is defined, so I say lambda goes to sigma of lambda. Sigma is some other parameterization of the curve. D by d lambda is obviously d sigma d lambda d by d sigma. And now let me just write down that equation in terms of sigma. So d2, well, let's do it on this board. Front. So if we change from lambda to sigma, we see that d2x mu d lambda squared plus gamma mu alpha beta dx alpha d lambda dx beta d lambda. Okay, so I'm just working out that d psi mu d lambda, right? Which is just d2, so this is d psi mu d lambda, right? With psi mu equals dx mu d lambda. And the definition of parallel transport on a curve meant that I had to put a psi in this gamma, multiplying by, this is just psi beta. Psi beta, and so the parallel transport of the covariant derivative of the tangent vector is the following, and this is given by the okay. So let me just. Move that one down, that's the front. So, of course, this is true. And so if I differentiate that twice, yeah? Yeah. Yeah, thanks. Okay. So if I take that expression and differentiate with respect to lambda, what I get is d2 sigma d lambda squared, dx mu d sigma, that's the first term, okay, coming from here. And then I have d sigma d lambda squared d2x mu d sigma squared. Okay, so this term, d2x d lambda squared, produces two terms, the d2 sigma d lambda squared and the d sigma d lambda squared. This term just produces one. So this is gamma mu alpha beta dx alpha d sigma dx beta d sigma. And we want this to be 0. Okay. This term here is f of lambda. Sorry, I said it the wrong way around. I want this one to be 0. Okay. This term, we want this to be 0. To be 0. But the psi mu d lambda was f of lambda dx mu d lambda. Okay, so to make it 0, and dx mu d lambda is, of course, dx mu d sigma d lambda. So what I want is to choose sigma so that this term is precisely equal to that term. So choose sigma so that d2 sigma d lambda squared equals f of lambda d sigma d lambda. Okay, so if I make that choice, then it will follow that the geodesic equation in the sigma coordinate is just the one we had before. So that's easy to do. This is a second order ordinary differential equation, so you can solve it with an integrating factor. So d sigma d lambda is e to the integral f of lambda d lambda prime, any constant here. And so sigma equals a integral d lambda e to the integral, let's call that lambda prime, f of lambda double prime d lambda double prime. Okay, so that's the sigma I need to choose. Sigma is only defined up to affine transformations. That's why it's called an affine parameter. All right, and an affine transformation is one of the form sigma prime is A sigma plus B, where A and B are constants. So obviously, if if sigma satisfies, if we choose the sigma parameterization so that this equation is valid, then if I transform sigma further by this amount, the equation remains valid. Okay, that's actually obvious from here because this involves 2 powers of d sigma, this involves 2 powers of d sigma. So if I just change sigma by a constant, the equation will stay valid. By choosing A and B, we can always arrange that G mu nu dx mu d sigma dx nu d sigma equals constant. Sorry, I said it the wrong way around. Let me say it again. In the affine parameterization, d2x mu d sigma squared plus gamma mu in an affine parameterization, gamma alpha beta dx alpha d sigma dx beta d sigma equals 0. This, of course, is just the statement that d by d sigma of dx mu d sigma equals 0. And this implies that d by d sigma of g mu nu dx mu d sigma dx nu d sigma so this is a derivative. I haven't proven that, but you can check that it is a derivative in the sense that if I act with it on various pieces in here, I can use the product rule. This is equal to the following. Yeah, I'm jumping ahead a little bit, I'm afraid. D alpha g mu nu dx alpha d sigma. I'm just going to write something down and I'll justify it in a second. Dx mu d sigma dx nu d sigma. Okay, because so it's plausible. If this guy's a derivative, well, the derivative of dx d sigma is 0, so differentiating these two terms gives nothing. The only term is this term. And this term actually equals 0 because the covariant derivative of the metric is 0. Okay, so let's just prove that. The covariant derivative of the metric is equal to, in fact, I will show that equals 0. I will show that next time. An easy argument that the covariant of the derivative of the metric must be 0 is the following. Covariant derivative, what is it? Well, it's ordinary derivative plus some gammas. Okay? Pick some locally flat space-time coordinates. In the locally flat coordinates, the gammas are all 0, and the first derivative of the metric is 0. So in the locally flat coordinates, that covariant derivative is 0. But it's a tensor. So if a tensor is 0 in one coordinate system, it must be 0 in all coordinate systems. So it actually has to be that, this covariant derivative of the metric is 0. So what this means is that, now, when I write this down, you see I have capital D by d sigma. But the quantity in the brackets is a scalar. It doesn't have any vector indices at all. So actually, this equals to ordinary derivative. Because that's a scalar quantity. And so it follows that g mu nu dx mu d sigma dx nu d sigma equals a constant along the curve in the affine parameterization. Okay? And we can choose that constant, can choose this to be -1 for time-like curves, 0 for null, +1 for space-like curves. So in an affine parameterization, I can pick this quantity to be plus or minus 1 if the curve is time-like or space-like, and it's 0 if it's null. Now, if it's null, it's telling you that you can always do affine parameterizations, reparameterizations on null curves, and there's actually no way to, that's just a choice. You always have that freedom. There's no special choice for null curves. It's just a matter of convenience, how you pick lambda, and they all satisfy the usual geodesic equation. So I think I've run out of time, so let me just ask for any questions, and then tomorrow we're going to use this to do some of the simplest predictions of general relativity. We'll see how the Newtonian limit comes about, how we get the effect of gravity from this metric, g mu nu. And then after that, we'll do a little more math. We will do curvature. We'll understand those second derivatives of the metric, how they turn into the Riemann tensor. And then probably around Thursday, we'll be doing the Einstein equations and learning what determines this g mu nu. So any questions about this material? Yeah.
Is it possible to write an action
for the massless particles? Yes, it is. It's a little more involved, but I'll tell you briefly what it is. You see, the nasty thing about this action is it has square roots. Okay? When you do quantum mechanics, that's a very ugly feature, because basically in quantum mechanics, this particle coordinate will want to explore all of its configurations. And to arbitrarily say it's not allowed to go into the null, if the argument of the square root is positive, it's not allowed to go 0 or negative, arbitrarily is a very ugly thing to do. Okay? Essentially, this is what Dirac wanted to take the square root of the Klein-Gordon operator. He wanted, and he couldn't just take the square root, okay? Because the square root is very ugly, and to this day, no one knows how to quantize something when you have square roots around. Basically, it introduces branch cuts and all kinds of mess. So this action is fine for classical particles, but when you discuss quantum particles, you want to get away from it. And so there is a way of doing it. Let me just describe it briefly. It's something which in string theory is known as the Polyakov action, but really it wasn't invented by Polyakov. It was known a long time before. But let's call it that anyway. So the way we define this action is as follows. No square root. Yeah, let me write it this. Okay, so no square root. Now that's kind of ugly because now this depends on lambda. Okay, so the d lambdas do not cancel, so the answer is not invariant under reparameterizing the curve, changing one lambda into another. So you introduce the following trick. You introduce some function, e of lambda, which you think of as an additional field living on the curve. Okay? It's not a field with any dynamics, but it just sits there on the curve. It can take any set of values you like. The only real important property of E is that d lambda E of lambda should equal d lambda prime E prime of lambda prime. So if I change coordinates on the curve, the E prime of lambda prime should equal d lambda prime E of lambda. So it's kind of, this is also called an Einbein. Okay, so the Vierbein was this 4-index 4-vector. This is an Einbein. It's a 1-index 1 vector. Okay. So you introduce this other field. Now, so then the idea is this is my action. It is invariant under reparameterizations now because I transform this E. Okay? If I vary this action, delta S equals 0, well, there are two variations I need to do. One is with respect to X. Okay? And what I'll find here, so delta S will be basically the geodesic equation times delta X. And by the way, it'll be the geodesic equation where derivatives involve 1 over E d by d lambda, because that is the reparameterization invariant derivative. Okay? The geodesic equation with derivatives in that form. So I invite you to do the variation. You'll discover that's exactly what you get. The second variation is with respect to this E. Okay? And this is going to give me, so if I vary with respect to E, I'm going to get g mu nu dx mu d lambda dx nu d lambda times d lambda over E squared, delta E with the minus sign. And this has to be 0. Okay, well, that imposes the condition that this equals 0. So this is a good action for massless particles, has no square root, gives the right formula. By the way, this is E d lambda, E d lambda. Okay, this is E d lambda, E d lambda. So it gives a completely reparameterization invariant constraint and geodesic equation. Okay, so that's a good action. Now you might say, whoops, what about the massive particle? Surely I should treat both together. And then the trick for the massive particle is to add another term. For the massive particle, we add another term, which is we add, let's see, to get the right answer, you have to put a half in here. We add m, let me see, m squared E, integral d lambda, with a minus half, I believe. Not sure about the factors, but something like that. So that, what is this thing? Well, this is a cosmological constant. If you do gravity, the cosmological constant in space-time is just a constant times the 4 volume of space-time. Okay, this is the kind of one-dimensional cosmological constant for the particle along the volume of its space-time. Okay, so it's a constant multiplied by the length of the world line, multiplied by the reparameterization invariant length of the world line. Okay, this is a strange thing. Doesn't mention the space-time coordinates at all. So now if I vary, I'm going to get minus 1 over e squared. From here, I get 1/2 g mu nu x dot nu over e squared with a minus sign. Okay, and then I'm going to get from here minus m squared delta e. Okay, and this will give me the constraint that g mu nu x dot nu over e squared is equal to minus m squared. Which is basically the same formula that I have there, that the 4 velocity squared is minus 1, except it's minus m squared here. You could always re-choose the parameterization to get rid of that. Then the other sort of amusing thing about this is that having worked out the equation for E, I could solve for E. See, this is the equation of motion for E. So why don't I just solve for E? I would say that E is equal to 1 over m times square root of minus g mu nu x dot nu. Right? That's the solution for E. Now, if I put that solution back in the action, what I'll discover is I get exactly the square root action. Okay. So E is this extra degree of freedom. You can eliminate it using its equation of motion, and you recover exactly the original action. Okay. So these are kind of games you can play with actions. The square root or the non-square root, but if you have the non-square root, you need this auxiliary variable E. And that's the way people do string theory, is that they don't have the square root action, which is called the Nambu action. They have the non-square root action, which is called the Polyakov action, but then you've got to integrate over E. Okay, I bet you wish you hadn't asked that question. Any other questions? Mm-hmm.
Can you solve the equation of motion for E in the massless case?
No, that's a good, let me think about that. So in the massless case, this is 0, right? Well, no. I mean, you see, in the massless case, E is undetermined. It's completely undetermined. And that's the same thing as saying the parameterization is arbitrary in the massless case. There's no special parameterization in the massless case. There's only affine parameterizations. So E is completely undetermined. We just get this equation, g mu nu x dot nu equals 0. It doesn't depend on E at all, so you can't solve for E. Okay, and this is true in any parameterization. Okay, good questions. Any other questions? It'd be nice to do some quantum mechanics in this course, but I think it's beyond the scope. Is there a tutorial this afternoon? Yep, okay. So I'll be around at 2 again briefly, if you have any other questions.